Alright guys, so in today's video we will be talking about, so you already know, right, before going into what today's the topic is, you already know that we have been following a microservices series where we have done so many things so far. So before starting off our video, I have one request to you guys. I have seen like in our channel 65% of people who visit our channel and watch our content but they don't subscribe. It's my humble request to you guys, please subscribe to my channel. So it will act as a motivation for me, right? So I can come up with a lot of interesting topics and try to teach you end to end. All right, so in today's topic we will be discussing about this part majorly, where we will understand what is the Kafka. We will also understand the event driven architecture aspects, and we will also try setting up one in the same way that people set it up in the organizations professionally. All right, so just for reference, I don't know if you are aware of it, this repository, by the way, is my GitHub repository, which is public, and we're trying to deploy this architecture. So far we were able to deploy this Kubernetes cluster, and we also deployed this VPN gateway, and we also deployed this VNet. We also I believe 1 or 2 days back I released one video where I tried explain setting up all the CI/CD pipeline. If you are interested enough to watch CI/CD, please go to my videos and you will find one video related to it. All right, so let's move on. So here in this architecture, you see this, we have this database, right? And then we have this Kafka connect source connector, and then we have this Kafka cluster, and then we have the sync connector, and then with this we have Cosmos database. So majorly in this video we will be talking about this part. Don't go to the technical words, very soon we will be talking about these, but we won't be deploying this Kafka sync connector and the Cosmos DB. However, we will, right? But after a couple of videos, because this is related to change data capture, today we will only deploy the Kafka cluster, the whole Confluent Kafka data platform, and we will also deploy one microservices to consume those events. We will try creating events, right, using Kafka Connect from the database as part of the data and the change capturing, and we will also talk about different aspects of it. All right, so let's jump off to our architectural design, and then we will move into the implementation, the deployment part. All right, so I already have this created, right? So before directly moving into the design part of architecture, let's first understand few fundamentals of Kafka. All right, so now so if you see here, right, I have mentioned Confluent. So Confluent is basically an organization who is pretty much deep into the real-time data streaming platforms, and they already have their Confluent data platform for the event streaming, which is totally based on Kafka applications, right? And then event-driven. So let's talk about event-driven. Let's talk about Kafka, the basic workings of Kafka. So event-driven is kind of a async communication system, because right, generally what happens in the client-server service request model, that we have a client, let's say this is your client, and then we have a server. All right, then this guy gives a call to server. All right, and that call will be based on will be an API, right? So when I say API, that means it could be a REST API, or let's say a gRPC. All right, so this guy will call the API of server. So this is your server. So directly write it here, and then this is your server. This will send a request to your server, and it's a REST API. What is REST? You can Google around it. This video is not around REST and gRPC. Now, eventually, when you do a REST and everything, your services make TCP connections with each other, all those handshaking and everything happens in the background, right? And then you send a request, then this guy will send you a response, right? Then and there. So this is your request. All right, so this is your request, and this is your response. All right, now the problem with this mode of communication is, let's say what happens when your server takes a lot of time. Your server talks to multiple different services, okay, and then this guy takes some time to send the response back, right? In this particular case, what will happen is your client will keep on waiting for the response, right? So there is kind of a delay involved. Or let's say there are multiple scenarios. It's not the only single scenario. Let's say this is service 1, this is service 1, and then I'll copy and paste here. All right, and then this is service 2, this is service 3, and this is service 3. Now what happens is when client is sending request to server will take some time, because the kind of processing, the kind of API it has exposed will take some time to send the response back, to prepare a response and send it back to the client. This is one scenario. Second scenario, think about the case that you have multiple clients, the consumers, the speed, the rate at which consumers are creating requests to server is far much high than the capacity your server can consume, right? This is a second scenario. So in those kind of scenarios, you will have to come up with a communication mechanism where client does not have to wait, or server doesn't have to send a response then and there, right? So what could that be? What could be the solution? So this particular mechanism of communication between two services is known as sync communication. All right, this is known as sync communication. Now let's talk about the solution of the problem we just discussed. There were two problems we discussed. One is your server is kind of slow comparatively to the rate at which your client is sending requests to the server. First and second, this is second. First, let's say server needs some time to prepare a response and send it back to the consumer. All right. So the one solution of these problems could be async communication. Now let's understand what is async communication. All right, so now let's say you have one client here, okay, and then you have server here, okay. Now server doesn't want to send the response then and there. Server want you send me a request, I will send you the response whenever I am ready. All right, so this can only be possible with something in between, right, who will kind of take the request from client and send it to server whenever server is ready. So what data structure that could be? So don't think from the technology and all these applications perspective, think about the data structure perspective, think from the fundamental perspective. So one data structure solution would be queue, right? Because what queue does is queue works on the FIFO principle, first in first out. All right, so what you can do is you can introduce the queue in between, right? So what I'll do is I will introduce a queue in between. Okay, so now my client, or let's say there are multiple clients, right? So this is client 1, this is client 2. Now my client 1 and client 2 will send a request to my queue rather than the server directly. Okay, so this will send a message here, and the terminology I am using is a message. So your request, the payload you are sending to queue, let's call it message for some time. Okay, now this message will go to your queue. So this is your queue. Okay, now this server is listening from the queue. So now he's kind of listening. Listen. Okay, now server will, so now client 1 has sent a message X, a request X to the queue. Your server is not ready. Whenever your server is ready, server will consume that message X and will start processing the request X and will prepare a response, right? Now whenever the server will prepare a response, now how server can send that response back to your client, right? So one solution could be that when client X is sending a request, so let's say client X is sending a request, client 1 is sent a request, so this is your request payload, and then this is a callback URL is equal to X. So this is the concept of callback will come here. Now one solution would be client 1 will send a request to your queue, okay, and along with your payload, client 1 will also send a callback URL. Client will basically send a URL, And why it is callback, I'll tell you why it is callback. Whenever server is ready, server will prepare a response, send that response back to the URL which is X and which is callback. So what client one is saying, okay, you do whenever you are ready, and when you are done preparing all the response, you send it back to this URL, this address, and that what that address will be, that is callback URL. That is one mechanism. Or second mechanism, that this is your request queue, and then this is your request queue, you prepare another response queue. All right. So what you will do is you will prepare a response queue, okay, and then this will be your request queue in that case. Request queue. All right, in that case your server will send the response back to your response queue, and then the only major drawback of this kind of design is these guys also have to listen then on the response queue, and then async communication and everything comes with some kind of pros and cons, right? So all the drawbacks that you have associated with the async will also apply to client 1 and client 2. So system kind of will become a little complicated. So better way is you basically have a callback URL, right? So this kind of mechanism of communication among services is known as the async communication. All right, and which is pretty much famous these days, right? Many organizations are using it. Almost, I believe, most of the organizations are using it whenever there is something involved where server will take some time to process and prepare the response. So that was the concept of async. Now why we discuss async? Because the whole concept of event-driven architecture is kind of coming out from the concept of async communication. All right. So now let's discuss about event-driven programming. Okay, so event-driven, when I say event-driven is kind of, so let's say it's totally activity-driven based, right? When I say activity, that means that, for example, you have a watch and you're wearing that watch in your hand, and there is an alert happened because watch detected that your heartbeat has gone beyond this particular X limit. So that this watch will be a client. It will trigger a request. It will trigger a request to your server, right? So when I say a request, that means an event, right? So these are the basic scenario of events. That means event could be anything. Let's say you clicked on a button, that's an event, right? You created an entry into your database, that's an event, right? So everything is event. So event-driven architecture comes out of async communication, where when something happens, you will have to perform some activity, right? When user has been created into database, you send an email to your user on the email of user, right? Or you send a WhatsApp notification on the phone number of that user. So all the scenarios, right? All the scenarios will be event-driven kind of architecture. Or let's say there is a chemical factory where a lot of data has been generated about gas tank, and that data is being pushed to this queue pipeline, and then all those that this is the pipeline's data, and then at this particular time this was the chemical X, this was chemical Y. All this data is being pushed to your server. So those kind of events, you cannot just keep on hitting APIs in these scenarios. What you will do is you will keep on generating events, and then you will try to stream it. So you will set up a data pipeline where one guy will be keep on listening all these events, and then one guy will be keep on sending these events. So these are the scenarios where your event-driven architecture comes in. All right. Now let's talk about that. Now by this time, I believe we have already spent like 15 minutes on discussing about async communication and the event-driven architecture. Now let's quickly move to the design part of event-driven architecture that we will create using Confluent platform. All right. So to implement this, we will use Kubernetes service. So let's move on. And for a moment, let's think that this is your cloud architecture in Azure. Okay. And then you also have a database in it. So your database is Postgres database. So I'll say Postgres database and I'll create one. Okay. Now to this Postgres database, okay, and then you have your AKS cluster right here. Okay. Now in your AKS cluster, you have your business services. So you will have some pods. So I'll create pod. I'll create pod. pod, and then you will have this ingress pod first of all, because that's where all the routing and everything will happen. And then although you don't need this ingress pod as part of this data pipeline, because there's no point that you expose APIs or rerouting and all those things you do via ingress. In this particular case we don't need it. However, just for architecture's sake we are writing it here. And then create another pod right here. All right. Now everything is pod. So what I'll do is I will create, this is your Kubernetes cluster. So I will write your, let's say, Confluent. Okay, this is your Confluent. So I'll write Confluent platform. Your Confluent platform will have many pods in it, because everything comes in the Confluent platform as the pods and containers, right? You're using Kubernetes, everything will be a container. So here you will use also Kubernetes service. So I'll say Kubernetes service. I'll have one icon here. Okay. Now this is your namespace. You also call it a namespace. I'll name it a namespace. The namespace in which we are in is namespace is equal to retail DB. Okay. Now here I will draw a parameter, because that's not the actual line, so I'll draw it like this. Okay. And then this is your let's call it as the invoice consumer. Okay, I'll call it as invoice consumer. Okay. And then inside your Confluent platform, you will have many pods. So one pod will be of, I will only write the important ones. However, you will have multiple, right? So you will have, let's say this is your Kafka cluster, and then this is your Zookeeper, and then this is your pod. Oh, actually, before this, let's also understand the working of Kafka. We actually did not talk about Kafka, right? So what I'll do, I'll rename this to async, right? And then I will create another here, and I'll say Kafka fundamentals. So now Kafka is very interesting whenever you talk about Kafka. So Kafka, by this time you might have understood that Kafka is a messaging platform. All right. So a very special messaging platform. Why? It's very durable, right? No matter any fail is being happened within the cluster, your message will be there, right? It's very scalable. Why? You can have multiple number of brokers, that means multiple number of nodes, and then every node will have different partitions. So you have data at one partition, you will also have that data replicated to another partition. So that kind of scalability comes in the Kafka. All right, and the performance, it's high. It has a high latency. Very low latency, sorry, my bad. It has very low latency and it is very high performance. All right, so these are basic properties of Kafka, and then understood the basic working of Kafka. It works on an event log mechanism. So I'll tell you what is event log mechanism. So, or rather I will use something interesting here. All right, so now let's say this is your Kafka broker, all right, Kafka topic. Let's understand. Now it's very in depth. Now let's say you have multiple messages here. Okay, you have multiple messages here. Now I'll write many. Now let's say one message you will have here, 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 and then one right here, one right here, and then I'll copy another, I'll paste it here. Right, one here. So these are the messages. Now this is event log. When I say event log, think as a file. Everything is being written in that file, and when you write something new, that particular text or that particular message gets written in the end of the log, basically. So it's a log kind of file where you are keep on writing in the end of that log file, right? So, and now let's think that you have multiple consumers here. Okay, these are your consumers. Now this is your consumer 1, this is your consumer 3. Now the beauty of Kafka is this consumer, right? So Kafka is being distributed among multiple partitions, right? So the way it works is now let's say this is your Kafka broker 1, okay, and then you have Kafka broker 2, and then you have Kafka broker 3. All right, and then you write a big box, so it's your Kafka cluster, think. And then you have Kafka broker 1 here, and then you have Kafka. I'll come to the above diagram later, give me some time. And then this is your broker 1, and then this is your broker 2, this is your broker 3. Okay, now, and here you will have producers, right? You will have many producers. So let's call it producer 1, and then this is your producer 2. All right, so so each broker will have many partitions. So let's say you have created topic. So I'll tell you what is topic. So let's say there is invoice events topic, right? So the organization of invoice event topic will be distributed among multiple brokers, multiple nodes, multiple partitions. How? So the inside of this broker will be, let's say you draw it right here. I'm just trying to explain you in the depth. So you will have multiple partitions here, right? So let's say this is your partition 1, okay. Copy and paste here and copy and paste here. So I decided to go with 3 partitions per broker. So your one broker will have multiple partitions. Okay, so this is partition 1 and this is partition 3. Now this is the inside of one broker. Now each broker will have a design like this, right? That means each broker will have 3 partitions. Okay, now the distribution of invoice topic, let's assume for a moment that is being spent under partition broker 1 and partition 1. For a moment, let's assume this is where you are keeping track of all the invoice events. Okay, now also in the broker 2, this particular broker 2, it is under partition 2. All right, and then in broker 3, your 3, you have partition 1. Okay, so what it means is partition. Okay, so now every broker will have this kind of architecture, right? This kind of architecture. So I will copy this and I'll copy this and I'll paste it, let's say here. I don't know, but okay, for a moment let's assume these guys will be keep on writing in the cluster, your Kafka cluster, and then this Kafka cluster is made up of multiple brokers. This multiple broker has multiple partitions, so your one topic is being distributed among multiple partitions. All right, so okay, so I have created these 2 boxes as well. So this broker 1 have this distribution and then this distribution. Now as I said, now let's understand the working of Kafka, right? Let's understand the basic working of Kafka. Now what will happen is, I'll come to this diagram later in some time. First understand this architecture of Kafka. So this is a Kafka cluster. One second, I'll write it here. This is your, where is it? Kafka cluster. Okay, this is our Kafka cluster. All right, and then this everything is being managed by Zookeeper, because you see there are multiple nodes, there are n number of nodes. When I say broker, that means a node, right, which is nothing but a kind of a node, right? So now understand how everything is being managed, right? Everything is talking to each other with a coordination system. What this coordination system is, that coordination system is Zookeeper. So let's say you will have Zookeeper here, right? Zookeeper. I don't know if you know about Zookeeper. I'll give you a brief. This topic, however, this video is not it's not majorly on the Zookeeper, but I'll quickly talk about Zookeeper. Zookeeper is nothing but a coordination system. Many people use it as a service discovery, right? So all those services register themselves in the Zookeeper, so others can aware, okay, these are the services which are active. Or you can use Zookeeper as a coordination system where one node can talk to another node, right, in terms of different aspects, right? So that's how these guys are also talking. So Kafka cluster, you don't deploy Kafka cluster alone. Kafka cluster always, before even deploying Kafka cluster, you need Zookeeper, because that's how the different nodes of Kafka talks to each other. Okay, so now this is our Zookeeper. Now what will happen is, I'll write it here. All right. Now what will happen? Now you write a message X into invoice event, right? So these partitions will have topics. Okay, these partitions will have many topics. So I'll say group of topics. Okay, so each partition will have multiple topics. So let's say, I'll tell you what, there is a technical interesting term which people use to indicate these replicas. So let's say you have invoice topic, so you will have one invoice topic here, right? So you will have one invoice topic here. Let's say, just assume, let's say invoice topic. Okay. And then you also have this invoice topic you will also have in these partitions, and you will also have in these partitions, right? Now what will happen when the moment you write X into invoice element, so your Kafka will use kind of a round robin algorithm to distribute the write X into one of the partition in one of the broker. So for a moment, let's assume that that particular X gets written into broker 1 and partition 1. All right, now what will happen, and then for this invoice event you have in sync replicas is equal to 3. Now I'll tell you, that's what we are discussing, in sync replicas. Now what Kafka cluster will make sure that this value of X in invoice topic should also get replicated to one of these partitions. Let's say it gets written to partition 2, and it also gets written to partition 3. That's what I have written here. All right, so this concept of replicas, keeping multiple copies in multiple brokers of one data, is known as in-sync replicas, and that's what make the entire Kafka durable, right, and your scalable, right, and it's also tolerant from the fault. So your value of X is inside broker 1 partition 1, and then broker 2 partition 2, and then broker 3 partition 1. Now let's say this partition has a problem, or this broker node has gone down, but you still have that values from the partition 1 and the partition 2, so that value can be stored from here and there. That's how the system has become durable, highly available. Now second thing is the way it works, the way Kafka in-sync replicas work. The one partition for invoice topic values will be an active participant, right? So when I say active participant, and the other will be passive participants. When I say the other replicas will be read replicas, one will be write replicas. So how it will work is, so let's say for invoice event, your partition 1 is your write, so all the write will happen to partition 1, but the responsibility of this broker 1 is to replica this database to the other read replicas, right? That's how the entire system works. And then you have your bad guys here, right? You have your consumers here. So this is, let's say, consumer 1. So from where it is consuming messages, it is trying to consume messages from partition 1. Not here, here. All right, so that's how it works. Now it's currently reading it from the partition 1, but there could be chance that it can read from partition 2, because you have data here as well, right? And then it can also read the data from broker 1 partition 1 here. All right, so this data. Okay, so that's the organization of your entire Kafka cluster. Okay, and then I don't think if I missed anything. Okay, so Kafka also can guarantee the ordering of message, but you see there are multiple partitions, right? So Kafka doesn't guarantee the ordering of messages in among multiple partitions. So your consumer will be reading messages from only within one of the partitions. So Kafka guarantees ordering of messages within one partition only. Okay, within partition. But that's the core concept design of Kafka. Second thing, let's come to this point and see how Kafka works here. As I said, that Kafka is nothing but an event log. So assume as a log file, everything you are writing is being written at the end of that log file. All right. So let's assume that you have a log file here. So this is your log file, assume. Okay. And then when you're writing something, this is, let's say, data 1. Now you write something else, that becomes your data 2. All right. And then you write something else that will come to this end. Okay. And then when you write something else, you will come to data 4. So you assume that this is nothing but this is the event log, right? So this will be your data 1, and then this will be your data 1, and then this will be your data 2, and then this will be your data 3. Okay, now think from the consumer perspective. This consumer, let's say, is kind of working behind than this consumer. Okay, and then this, you also have this consumer. So there could be a chance that this consumer is reading from here. It's not necessary that it will always read from the latest message. It may be working with a delay, and then there could be chances that this guy is directly consumer from here, and then there could be chances that this guy is reading from here. Okay, so how your consumer knows that I have to consume it from here, I have to consume it from here, or I have to consume it from here? So this is where the concept of offset comes in. So for each consumer, you maintain an offset value. So let's say this is offset, this is 1, and then this is 2, and then this is 3. So your offset for consumer 1 is at 3 currently. So it will start consuming from 3, and all the messages from 3, right? And then consumer is at 2, that it will start consuming from 2, right? And then it will consume other messages. And same applies to consumer 3 as well. So that's the concept of offset. That's how your consumer maintains an offset. Now, you don't want to repeat all the messages in all the consumer. Let's say you have an invoice consumer application. For some reason, or for the horizontal scaling aspects, you have scaled your application. So you have created one invoice application, and let's say this data 1, your one invoice. You don't want your data invoice to be consumed in multiple consumers again and again. So there are multiple replicas running for invoice consumer. So the way because this is a topic, right? So the way topic works is, you have one you basically send a message, and all the consumer will get a same copy of that particular message. So that's the problem, right? If you send one invoice as part of data 1, what will happen? All the invoice consumer, which is 1, 2, and 3, will consume the same copy of your invoice. Now the problem with this approach is, all application will process the same message again thrice, right? Although that's the same message. So that's another problem. So that's where Kafka gives you another functionality of consumer group. All right, so all these things are connected with a consumer group. So this will be connected till here with a consumer group. So I'll say consumer group is equal to invoice processor, or let's say invoice consumer. All right. So now in this case, the way it will work is, for a particular consumer group, so my consumer 1 is also inside consumer in the same invoice consumer group. Consumer 2 is also inside consumer invoice consumer group, and consumer 3 is also here. So this data 1 will be delivered to one of the consumer, not all the consumers. Now let's say if I create another consumer here, right, and then this consumer has a different consumer group. I'll copy it here, and let's say this has payment consumer. All right. So now the data 1 will be delivered to one of the consumer right here, and or also to this consumer 4. So it will be delivered to one of the consumer from here, invoice consumer group, and it will be delivered to payment consumer. So that's how your event log works in Kafka, and that's how you get all your the benefits out of Kafka, and that's why your Kafka is much famous nowadays. Almost most of the organization who want to implement the event-driven architecture have now started using Kafka, right? So that's the beauty of Kafka, of everything that we discussed. I think we have already covered a lot of theory part and the design aspects of Kafka, the fundamentals of it. So probably I will not cover the implementation deployment of event-driven architecture in this video. I'll probably create another one, right? So if you have seen enough theory, if you want to see the implementation and the deployment, probably refer my next video. All right. Thank you guys.